Welcome to your next laboratory, and this laboratory is going to concern the density meter. And depending on how you've been structured, this could be your first lab involving density, or it could be your second lab involving density. And the reason is because we cannot bottleneck at the machine. The problem with the density meter, okay, not the problem, it's very automated, which makes our life much better. But the true problem of this density meter is time. That's right. It's going to take forever to run a sample. So I can actually go into a lab and I can get a volumetric pipette and I can pipette 1 milliliter of my solution onto a balance and I can provide a mass. And folks, that mass is mass per 1 mil, which is gram per milliliter, which is also density. And within a matter of 1 to 2 minutes, I can have you a density value for a liquid solution. That's not the case for the density meter. The density meter will take probably greater than 5 minutes in order to load a sample, type in the name of the sample, type the temperature of the sample, let the machine come to equilibration, press run, allow it to do multiple density samples, get my values, print the report. Oh gosh, you see where I'm going with this? Density meters are great. They're great to automate a laboratory that uses density often. The problem is that it takes forever to get data from the instrument. And that's why we split you up in 2 different groups, and we allow one group to focus on the density meter, and we allow the other group to focus on the other density tests that have to be performed during this time. Now, I want to tell you a little bit about our density meter, kind of showcase a little bit about where our instruments come from, because that's part of our program, right? We want to make sure that you understand the different types of manufacturers and the different types of pieces of equipment that are out there for our purposes. And here's a website. This is Rudolph Research Analytical. And the Rudolph Research Analytical website is going to basically be a showcase of all of the equipment that this company manufactures and that they make. So if you go to rudolphresearch.com, this is going to be a website that will show up. And if you go into products, you will see a number of different types of products that they offer. One, of course, is the density meter that we have in our laboratory that we'll use today. The others are going to be things like refractometers and polarimeters and saccharimeters and automation, all of the alcohol test RI, all of these other pieces of equipment are going to be listed, but today we're only going to be focused on the density meter, and that is it. So under the density meter, you will see a couple of different versions depending on how old the machine is or what you need for capability purposes. They make different models, just like they make different model of cars on a car lot or different models of computers depending on what you need to use it for. They also have different versions and variations of density meters. So this is where you're going to be able to find more information about the density meter, more information about the purpose of a density meter and why we would use it in industry. All right, so this is a very good place to kind of start, but I also need to incorporate a little bit of background about what you'll be doing with this instrument. All right, so first and foremost, I want you to take a look at the price tag down here at the bottom. Folks, these things do not come cheap, and we're looking at over $10,000 for a basic model. And then depending on the bells and whistles that you want to add on to this thing, that cost will significantly grow higher. It will go more and more and more, and before you know it, you're in the $20,000 and $30,000 range. And this is maybe bad news for a lab, depending on how often they do density measurements. All right, so this is a piece of equipment that I would say is kind of floofy for us. And the reason that I say that is because I know that we can do density by hand. But folks, part of this program, if you're in the chemical technology program, is to make sure that we align you with industry. And depending on where you go, you could be using an automated density meter. And we don't want to take that experience away from you. So we sunk in a little bit of money, and we're going to showcase the automated density meter for you. And you might never ever see it again. But know that our lab has the capability for it. Know that any time that you need a density for any lab that you're doing, this instrument is there for you. And keep in mind that depending on where you work after you graduate, you could be using a density meter for whatever purposes that they need to do. All right, so here is the use of the density meter. I'm going to scroll down a couple of things, and we're going to talk about some terms. The first term that I want to focus on in this video is this thing called a calibration. Some of the other terms you've seen before already, like standard deviation and maybe density and specific gravity, but calibration is maybe a new term for you. And this is a concept that our instrumentation, all right, we've got some instrumentation in the lab. There's tons of it, actually, right? We have over $1 million worth of instrumentation in our lab facility. And this instrumentation has to be calibrated, which basically means you have to ensure that it works. All right, so let's say that I'm flying down the interstate and a state cop basically sees me and catches me on the radar and says, "Sir, you were speeding. You were going 100 miles an hour in a 35 mile per hour zone." Well, if it's not 35 if I'm on the interstate, but you get the idea. Well, one of the ways that people could maybe try to beat the system is to say, well, you know, you were using a radar, and that's an instrument. So when was the last time that your instrument was calibrated? Can they provide that result? Can they provide that report? If not, then how are you going to prove that the radar was actually reading the correct miles per hour? In other words, let's say they clocked me in, I can go 5 miles over. So if I'm driving on the interstate at 75 miles per hour and I'm at 80, and the cop clocks me in at 83, okay, where's your proof that your radar was actually your speedometer or your speed checker, whatever they call them, whatever they use? Where's the proof that that instrument was actually calibrated the proper way? How do you know that that was 83 and not 80? Or how do you know that was 83 and not 79? When was the last time that this was done? So all of our equipment in the instrumentation room has to be calibrated. Even our analytical balances that you've used so far, they have to be calibrated. That was the purpose of the calibration weights. This is kind of the process that we go through in order to do this. So we have to ensure that our instruments are providing data that is scientifically solid, which means we have to make sure the instrument is working the proper way. And this we have to do before we do any kind of measurement at all, period, using that piece of equipment. All right, so this is the idea of calibration, and you will be doing calibration in this particular lab. The other page that you're going to see on this lab document are these different units that come along with the concept of density. People will use density for a number of different purposes, depending on the types of samples that they're analyzing and depending on the types of units that they want to report for their particular field of study. So for instance, if I'm in the beer manufacturing process, I'm probably doing density, and they probably do something other than grams per milliliter as the lingo that beer manufacturers know. If I'm in the winery section, right, I'm making wine, I'm producing wine, I'm fermenting wine, I'm bottling it up. Well, there's probably a certain way that we report density, and it might not be the scientific laboratory way. It might be their own units that they like to talk about and they like to discuss. So this is the problem with density. There's so many different options out there that we can report density in. And folks, this is just kind of a very run-of-the-mill general pull of different ways that we could maybe talk about density or represent density in a different way. So for a laboratory, most of the time we're going to be focused on gram per milliliter. And this is the unit that will come along with density every time that we report one in a proper scientific laboratory. But again, depending on the field and depending on the laboratory in that field, you might be required to report these values or concentrations or densities in a number of different ways. So just kind of an FYI thing, that stuff might be coming. So this is just an idea of kind of getting you prepared for what else is out there. All right, so let's take a look at Part A. Part A is going to say, you're going to work in groups. Okay, I know. Some of you get excited and some of you don't. The reason that we have you work in groups is because these things take so long to run that if we required everyone to inject every sample and we have a full class, folks, this could take like a month. I mean, we definitely are not going to be there for a month doing the same lab over and over and over. What are you going to do when other people are already finished and you're finished and you're waiting on other people to finish? We've got to do something. So we're going to work in groups, and we're going to break you off into a smaller group, and your group will be responsible to provide all of this data. The thing, though, is that each person in this group will have to inject at least one or more, at least one sample. We want your hands on the machine. We want you to work with the instrument. We want you to inject samples. We want you to print data. We want you to title and save data into the instrument. We want each person in the group to do that. So once everyone gets a stab at it, then you as a group can decide who needs to pick up the slack or who needs to inject another sample and so forth. So that is up to you, but we want at least every person to inject at least one sample in your group. All right, so Part A is basically setting up the calibration. So for Part A, it says turn on the density meter. Well, duh. I mean, we know we're going to have to turn it on, for goodness sakes. But there's a reason that it's in here, because chances are there's someone in some year that said, my density meter doesn't work. Well, that's because you didn't flip the power button. Okay, so it's in there for a reason. B, set the temperature of the instrument to 20 degrees, and then name the sample. C, with nothing in the chamber, only air, perform a density measurement and record that data and print off that report. For D, now change the temperature to 25 and add another name. And then for E, with nothing in the chamber, only air, you're going to do another density measurement and you record that value and you'll print that report as well. So A through E basically tells me I'm going to take air and I'm going to get the density at 20 degrees, and then I'll get the density at 25 degrees. That's basically all that it's saying. And I just want to print my reports as proof that I have done these density measurements with the instrument. We have to have proof or it's not done. All right? So next section, F through J, is going to basically do the same thing, but this time you're going to inject a sample of deionized water. All right, so deionized water is going to come from our system, our deionized system in the laboratory. Make sure that you use deionized, not tap water. And while you have it at 25, we're going to insert a sample of water into the instrument, and then we're going to record the density at that temperature. Then we'll change the machine back to 20, and we'll do it again. You can leave the water sample in there. Doesn't matter. You can leave it in there. And we'll report another density. Once more, record that into the data table and print off that report. So we do air at 20 and 25, and then we'll do water at 20 and 25. And this will complete the calibration portion of the machine. Okay, well, wow, what does that even mean? I mean, we're just injecting water and air. Yeah, I know, but it's water and air. So the purpose in doing this, we know what the density values need to be for air and water at these two different temperatures. So this is the way that we make sure that our density instrument is reporting a proper value when it shows us a number on the screen. So air at 20 and air at 25 need to both be 0.0012 as far as the density is concerned. If I do not get a number that's 0.0012, then this could be a problem. If it's very far away from this number, then that means my instrument's not calibrated, and that means I need to work on it and I need to fix it before I use this piece of equipment to do any data. Water's the same way. We know what water should be at 20 and 25 degrees, And here are the density values at those two particular temperatures. And once more, this is my third and fourth data point that I use to ensure that my instrument is providing me the proper answer. Notice this happens before I run any kind of sample at all. I want to make sure that my instrument is calibrated. Now, error. Okay, we know that there's error involved in the laboratory environment. We know you're going to mess up. We know the balance is going to mess up. We know volumetric pipettes have errors. We know burettes have errors. We know micropipetters have errors. Errors everywhere. And the density instrument could have errors as well. So we can't really just say you have to have 0.0012 or it fails. We can't really do that. It has to have 0.9982 or it fails. No, that's not really how this works. So we have to give you a window. A window has to be acceptable, taking into consideration that error is in play, and we need to account for that. So over here in this column, you're going to see an accepted, right there, you're going to see an accepted range that the density meter can provide you. So for instance, let's say I do air at 20 degrees and I get a density of 0.0013. Well, I take these two numbers and I subtract them. 0.0013 minus 0.0012, and I'm going to get 0.0001. Well, the accepted window here is 0.0001. So, ding, ding, that passes. That's a very good job. It passed that particular data point. All right, so then I go into air at 25, and my instrument gives me 0.0012. Well, it should be 0.0012. I subtract these two values, and I basically get a difference of 0. Okay, well, the accepted window is 0.0001. I'm below 0.0001. I'm at 0. There was no difference in them. So, ding, ding, that works for me. So the instrument passes that one as well. Then we get to water, and let's say water at 20 degrees should be 0.9982. And let's say I get a 0.9990. Okay, I'll write that into my data table. I take the difference, 9982 from 9990. Okay, well, that's a 0.0008. Uh-oh. That difference is way higher than the accepted window that should be on that instrument. So I'm going to have to that data point, which means that there is a possibility that my instrument is not calibrated, and we need to clean it, we need to maintain it, we need to get in and tinker with it, so that way we can get water to read 0.9982. Maybe my water was just a filthy, nasty water sample that I've not changed in a while, right? So I'm going to get fresh deionized water, and I'm going to reattempt it. There's a couple of different reasons that this machine could give me a faulty number, and that could be one of them. Well, then I would do water at 25, and let's say that water at 25 at 0.9970, ding, ding, let's say that passed. Well, all of a sudden I get one data point that's kind of wonky. Well, this could be maybe an injection error. This could be a user error. Maybe I didn't put the sample in the proper way. Maybe I had air bubbles in the sample chamber that's going to be a problem for me. Okay, so this is kind of the idea of the calibration and the purpose of the calibration when we do it. All right, so for part B, after you make sure that this instrument's calibrated, if you have done the first part of the density, you're going to be using the same 4, 8, 12, and 16% concentrations that you did in that particular lab. If you've not done that first part yet, there will be salt solutions that will be made, and they will be 4, 8, 12, and 16%, and they should be near the density meter. And it's going to be your job as a group to inject each one of these, what we call standards, because they're known concentrations. So standards are also known concentrations. That's why we call them a standard, and that's what the bracket X will stand for. And one by one, I'm going to inject the sample in, and I'm going to make sure that I visually see that sample on the screen, and I'm going to make sure that there are no bubbles. That's very important in the density meter, the sample chamber at least. So if I make sure everything looks good, I'll hit run, and that machine will report a density value for the 4%. I repeat that with 8, I do it again with 12, and I do it again with 16. All right? So this will complete my standards and the densities for those standards. And then I've got one more part left, and that's part C. And this will be an unknown. All right, so we're going to provide you a sample. This will have a percentage. You will not know that percentage. We do. We made it. We know what should be there. And we're going to allow you to run that on the density meter, and you'll get a density of this one as well. So there could be maybe a couple of different unknowns that get passed around depending on what we have in there circulating at the time. Just make sure that you write down the unknown code or the unknown number if there is one provided. Once more, just like before, make sure there's no air bubbles, folks. Air bubbles are going to be bad. Nobody wants the bubbles. And make sure that you overfill the chambers in each and every case, meaning, don't just push enough sample in there to fill the chamber. You go another extra 3-4 milliliters through, and that way you will ensure that that sample chamber gets flushed out of the old crappy stuff that you don't want in there anymore, and your new sample is going to go in to get measured. If not, you could get cross-contamination issues, and that's something that we want to stay away from. Finally, part D is going to say, now that you have all of this, go in and generate what we call a calibration curve using the data that we have basically obtained from the lab experiment. So here is Excel, and I've just opened up a new worksheet. That's really all that I've done. So this is the home screen of Excel when I begin a new workbook. And I'm just going to randomly click in here at one of the cells that doesn't really matter. And I'm going to type in 4 and 8 and 12 and 16, right? Those were the standards that they told me to run. So these are the starting points that I'm going to use to make my calibration curve with. And then the directions tell me to match that with the density value. So I'm just going to make these up, all right? So I'm going to do like 1.02, and then 1.04, and then 1.06, and then 1.08. All right? I don't know. You might not get those values, and if not, that's okay. You use what you obtained in the lab. So once I type in the percentages, notice that I did not type the percent key in. Okay, these are 4%, 8%, 12%, 16%. These are percentages. So up here, I can type in the actual percent key if that's what I want to do. So I'll do it there. And then here is going to be density. So this is how we make a calibration curve if you've never made one with Excel before. I've entered my data. Everything in this column will be placed on the x-axis. Okay, that's the axis that goes left and right at the bottom. And then everything on this column will be plotted on the y-axis, and that's the axis that goes up and down. So I'm going to highlight the data, and I highlight both columns, and it's staying highlighted. Up here at the top, I will then go to Insert, and then under the chart category, I will see a chart that looks just like a bunch of dots. So I'm going to click that. And this is what we call a scatter plot. And there's a couple of different versions that I can do with scatter plot. So as I move my cursor over, there I see just the dots. And here I see dots with lines. And there I just see the line. Here I see the dots with very straight, jiggity-jaggedy lines. And then here I'll see no dots, but with jiggity-jaggedy lines if they're there. Folks, the only thing that we use under the scatter plot are just the dots. That's it. That's all that we will ever use in our program. We will not use any of the others for any reason. So we're going to click the scatter dot, and this generates a chart that we call the calibration curve. All right, well, if I wanted to be fancy, I can. Let me show you how to be fancy. Okay, so I'll go up here to the top, and I'll click this chart title. And I want to name this just so that people know what this is. So I'm going to put salt graph. All right, you can name it whatever you want to name it. I don't really care. Just name it something. So there's my title. So down here at the bottom, these are my percentages because that's what went into the first column. And then on the y-axis that goes up and down, those are my densities because that went into the second column. So I'm not yet done with this calibration curve. So what I need to do at this point is hover over one of the dots. It doesn't really matter which one, just one of them. I don't care. And click that dot. And when you click whichever dot that you choose out of the lineup, all of them get highlighted. You see that there? All right. While you're over that dot, you're going to right-click with your mouse. And when you right-click, this gives you a shortcut. And that shortcut is a trend line. So you're going to choose Add Trend Line. All right, so when you do that, I'm going to shift this over just so you can see it. This box will show up. These calibration curves that we do most of the time in a laboratory, they should be linear. So you want to make sure that that's checked. And then down here at the very bottom, you're going to choose Display the Equation on the chart. And then display the R-squared value on the chart. And there they are. So this is an equation that we call a linear regression line, linear regression. And this R-squared value is something that we call a correlation coefficient. So linear regression line and correlation coefficient. What we're going to see here is that 1 is perfect. Folks, if I get a 1 for the R-squared value, this is a perfect line, which means that your data and your sample prep and your standard preps and the way that you ran them were perfect. I mean, you deserve a cookie if that goes on. We might even take you up on that offer and we might give you and buy you a cookie or maybe a brownie. Depending on how good is good and how many times you hit it, we might upgrade to a brownie. But if you give a 1 correlation coefficient, or R-squared, this is a perfect set of data that we really, really like to see. So it makes us feel good about our measurements when we get those. But this Y value, this Y equals 0.005x plus 1 is what we call our linear regression equation. So what is the purpose of this equation? This is what we do with it. In one of these parts, you took an unknown and you received a density of that unknown. Let's say that this was 1.05 for my density. Okay, well, what's the concentration of this? I mean, that's what we're after. How do I relate that density value to a concentration? Well, that's the purpose of the calibration curve up here. The purpose of generating that curve is to establish a relationship between the signal, which is the density in this case, and concentration units. So if it's 1.02, it should be a 4. If it's 1.04, it should be an 8. If it's 1.06, it should be a 12. Well, what about 1.05? That's not one of these. No, it's not. But look, 1.05 would be right in here, right? So this number is kind of in the middle of those two. So in the middle of 8 and 12, maybe 10-ish, somewhere in there, it gives me at least an idea of where this unknown concentration is going to be. The purpose of the equation is to allow me to mathematically solve for that. So y, the y represents the y-axis. What did you plot on the y-axis? Well, you plotted the density values. So if you did an unknown and you got a density value, then that density value needs to be plugged in for y. That is how you need to think about this, right? I plotted density on y, therefore the y variable is going to represent density. So my density is 1.05. All right, so 0.005x plus 1. All right, so there we go. And now I need to solve for x. All right, so for those of you rusty with math, let's do it together. I've got no problem with that. Here is the equation. You need to solve for the x variable, which means that you need to get rid of everything else around x first. So that means this 1. So I'm going to subtract 1 from each side. You do the opposite of. So plus 1, the opposite is minus 1. All right, so 1.05 minus 1 is 0.05 equals 0.005x. Okay, now you still do the opposite of. Solving for x, 0.005 times x. So the opposite of multiplication is division. So we're going to divide by 0.005. All right, so there we go. And I'll bring up the calculator just so that you can follow through with me. And maybe you've got one there in front of you. So if you want to do it too, be my guest. There we go. Let me put it on the screen. So I'm going to take 0.05. And then I'm going to divide that by 0.005, and then I hit enter, and I'll get a 10. Look, it's exactly what we expected, right? So we knew this just by eyeballing it. This value is probably going to be a 10. And I did that because I knew what my density for my unknown was, and I compared that to the standards and those known concentrations for those standards. All right, so that's what this basically lab section is going to get you to do. It's going to get you to inject standards, inject an unknown, make a calibration curve like this, do a little bit of math, and then figure out the unknown concentration based on the values that the density meter provided you. All right, so what you're going to see are a couple of questions at the end of the sections. It's going to be basically what if questions. What if your errors were really high? What if you had a data point that didn't quite match? You know, what are some of the problem areas that people might see when they use the density meter? Those are the types of things that these questions are going to ask you to do. Notice also here concentration. I've put a 0 here in the data point, and you know, quite honestly, 0 does need to get included in the calibration curve. I did not include it here, so that was my mistake. But when you plot your data, you will include the 0 mark. You will include the density of 0% salt, which is pretty important. All right. Okay, so there's the laboratory objective with the density meter, and I think it's pretty straightforward. I think it's very simple. It's a group effort. Just make sure that everyone gets a chance to go through and inject on the Rudolph Research density meter, and we'll be okay. All right. So in the meantime, what will happen is that you will probably juggle this with another lab that we're going to call the copper cycle. So as you're waiting, because this will take a couple of minutes at least for each person to inject a sample on, and you've got calibration standards and you've got standards from the salts and unknowns. This is going to take a little bit. So what do you do while you wait for everyone else to get their data finished, so that way you've got data to take home and do stuff with? Well, you're going to be working with the copper cycle. So you're going to be juggling the copper cycle laboratory experiment along with the density meter lab experiment. And when it's your turn to go run on the density meter, someone will come and get you and say, it's your turn, you're up. You'll go, you'll analyze your assigned standard or sample onto the machine, print off the data, and then you'll just go and tag team the next person who is waiting in line to use the density meter at that point. All right, so good luck in the lab. I don't think you need luck. I think that this is just a matter of getting acquainted with the instrumentation and appreciating what the instrument is doing for you. So if you got questions, you know where to find us. We'll be in the lab. We'll be in the hallways. Who knows where we'll be, but we'll be around. So just come and sniff us out, and we'll come to your help, and we'll come to your aid. That's what we do. That's why we're hired.